Now we're going to go on to give you a preview of something that we're launching later this summer. We're calling it Lightbits on AWS. And this is really our take now, a fresh look at storage in public clouds. And we look specifically at block storage today. And we had a chance to take a step back, think about how block storage is used in public clouds, what types of applications it's used for, reimagine that, and then think about all the great technologies we built at Lightbits and how we could apply that to storage on public clouds. So if we think about block storage on public clouds, let's take a step back and think about some of the applications that they're used for today. A lot of them are similar to what we found on on-premise infrastructure. And another thing we noticed is that there's a whole category of enterprise type databases like SAP, like Oracle. And when we talked to some customers, those were actually some of the last technologies that they wanted to migrate into the public cloud. And the reason for that was, well, they're usually very core parts of their infrastructure. And so the requirements specifically for the storage on those applications tend to be more stringent. And they need a lot of those enterprise type features, which aren't always necessarily available on public clouds. And so when we thought about that, and we thought about how do we make block storage better on public clouds, we came up with a number of different things. First of all, it needs to be compatible. It needs to work with any type of AWS storage instance. There's hundreds of instances out there. If you need high performance block storage, you're fairly limited in the types of instances that can connect to those. And we found that using NVMe over TCP, we can now enable high performance block storage on any sort of AWS instance you wanted, from the smallest teeny instances to the largest instances. The clients that's on the client side. On the storage side, there's a lot of storage focused instances that AWS deploys. Many of them have those wonderful technologies from Intel today. And there's some that are geared to storage efficiency around capacity, some that are geared towards performance. It should be up to the customer to decide how they want to deploy, if they want to be capacity based or if they want to be performance based. So we'll work on any type of storage instance from AWS today. Again, we have to be able to plug into all the different orchestration environments like Kubernetes, OpenStack, and VMware. We need to have multi-tenant support, so administrators can now decide how they want to allocate and partition their storage internally or even externally. Need to have interfaces into the storage that are flexible so that you can customize them into your own infrastructure. So we have APIs and command line interfaces for that. There's a number of interesting things now you can do that we couldn't do on premise, like upgrades, for example, because we have flexibility of having instances almost magically appear when we need them. Rather than upgrading a live instance, we can just bring a live version of the storage system. We can just bring a new instance online with the latest version of Lightbits and insert that into the cluster and take out the instance with the older version of the software. We need to have monitoring that's flexible, that's easy to plug into different systems. And we have that so that you can choose to plug it into your own open source monitoring, into a monitoring system that's proprietary or based on the cloud provider you're using. Another benefit we have is that you can have the same storage system with the same protocols and the same interfaces, both in the cloud and on-premise as well. So you're not building two different types of management systems. Now, that was one requirement. You had to be very compatible. The other one was the data services. So how does your application engage? How do we bring some of these enterprise data services to the cloud so now you can be just as efficient inside of the cloud? And so we do that by allowing you to partition volumes like you would with any cloud-based block storage system. You can do that with Lightbits as well, where you determine the size. One thing you don't have to do is determine the performance in advance. We'll give you the full performance of the Lightbits cluster to your block storage volumes disposal. We have things that you can't do in the cloud today with existing products like compression and compaction. So you take advantage of that. If your data is very squishy, why not store less data in that case? Thin provisioning as well. So you don't necessarily need to think in advance what size volume you need. That's one of the decisions you make when you allocate block storage today. What if it was thin provisioned and you allocated a petabyte size volume, right? And as you filled it up, the cluster would allocate storage for that particular volume, and you would then grow the cluster rather than resizing your volume in that case. Snapshots and clones are things that today somewhat people might use more sparingly because they're fairly expensive to do in the cloud today. With Lightbits, you can take as many snapshots and clones, and we don't charge for that, right? And they're stored either locally on the system, or we're very flexible and you can store them inside of an existing longer term storage system like S3, for example, or perhaps you have another NFS system you want to storage to. You want to store the snapshot and clone to, you can do that too. You can define your own quality of service. If you have different types of services using your block storage, you can choose how you want to allocate bandwidth between them. You can also define your replication. In the cloud today, you buy storage and it comes with a preset amount of replication. Lightbits, you choose. Do you want 2 copies, 3 copies, 4 copies? Up to you. High performance, that's one area that we shine in for sure. Even when we compare our performance against existing block storage technologies today, we have extremely high performance. We have volumes that we've tested in the cloud that can go up to 1.7 million IOPS if you need something like that. And we also found that the same low latency I talked about earlier also exists in public clouds as well. And we can achieve that low level of latency so you can get those very fast database queries without needing to worry about the shared nature of multi-tenant block storage today. So those are a lot of things that we bring new to the table that customers didn't have before when you're running block storage in public clouds. Quick overview of how something like this works. So on the left, you have your compute. Could be running your database, could be running your data analytics application that connects within your own VPC, your own virtual private cloud through a TCP/IP network. This is the beauty of NVMe over TCP/IP. It'll run over any network today, and it'll connect to a Lightbits cluster that's on the right. Here I'm showing a 3-node cluster. You can grow that to any size you want. And those servers work together and they store replicas of the data across each other. They work together to ensure that the data has enough durability, that the SSDs are available. If one of them goes offline, they'll automatically add another node to that cluster so that you maintain that same level of replication. And they'll also work together to serve your queries. So if you want to read, we can read from multiple devices at once. We'll spread writes across multiple devices as well. That's how we get to this high level of performance from Lightbits.
So the storage, that is customer managed, correct? That's not something Lightbits is managing for us.
It is something that a customer will deploy in their own VPC.
Okay.
And it's managed through some automation, and the customer can also manage them if they want to.
Okay, but it's not a managed service that you're providing as Lightbits.
Not with our initial launch, no.
Okay.
Yep.
And do you already have a CloudFormation template or a Terraform file or something that will help you get this deployed properly?
Yep, and we'll show you actually how it's done.
Okay.
Yeah.
Is this using the I series, the i3?
It'll run on any storage instance in AWS. So we use i3ens, the new i4is with the Ice Lake platform from Intel. Yep.
Okay. Okay. All right. And you said it can spread the writes over multiple nodes. Do you have to put any kind of load balancing mechanism in front of it?
It's all done internally within the cloud.
Oh, it's all done internally. Okay.
Yeah.
Is there a controller that sits in the front that the other?
Nope, there's a service that's run on each node.
Okay. Is that something that's all handled by the client that has the NVMe TCP driver?
It's no, the NVMe TCP driver is part of the Linux kernel.
Okay. So I can't run my Windows workloads with this?
Windows will release support for NVMe TCP/IP soon. Yep.
Okay. Server 2022, maybe.
It's coming.
You can actually run that through VMware. If you're running VMware, you can run Windows virtual machines through and use the NVMe over TCP that is supported.
Gotcha. Okay. And this is showing a single availability zone. Was that just for simplicity's sake?
This is showing a single availability zone, a single VCP actually.
Is there any reason you couldn't stretch the storage cluster across multiple AZs if you wanted redundancy?
It's something that won't be part of the initial release. We're working on it. However, like any storage system, when you stretch it, then the performance will vary at that point.
Right. There's latency between the nodes that are here and here. So, okay.
But that's the idea. We realize that you got to have the data spread across.
Okay. Yeah, I mean, if you're gonna put them all in the same AZ, you could use what's the thing in AWS that lets you put
Placement
them
group.
all? Yeah, placement groups to get them all tightly packed.
Yep.
So we have the ability to put it in placements group, but from latency perspective, since we're using the same availability zone, we didn't see that much difference with the performance or latency if we're looking at performance or performance-oriented machines.
Okay. So that makes sense. So you have the possibility of losing all your nodes because they're in the same rack if something happens to that rack.
In a rare case, right? AWS give you a very good resiliency for their racks, but we know that things could happen. And if you lose a single rack, if you don't put it in a placement group, they will try to spread it across.
Mm-hmm.
And if you do it, it's unlikely that it will be on the same physical rack, but maybe in the same building.
Right.
Which still is an elevated risk.
Mm-hmm. Okay.
But again, I mean, typically, if you're not, I mean, you can't guarantee if they are in the same placement, availability zone, they can still be in the same building. You wouldn't know. They don't tell you. I mean, they typically don't let you control that side of it.
That is correct. And especially if you're going to use newer instances that for example, if you use the I4I, the Ice Lake, they're likely to put it in the same building because they're expanding their racks in that formal way. But they do give a guarantee of some durability to it. So it's unlikely that a whole set of racks, a row will die at the same time because they have redundancy and backup and power backups and so on. But there is that option. Still, we're not taking that into our consideration. So our system has resiliency with the replication. So if one of the nodes will fail, the other nodes will come in and immediately and swap to that same volume if it's replicated to additional nodes.
I can see you're using a number of Intel accelerators there. Yeah, you're using the Intel 800 Series NICs, the Optane PMEM. The 800 NICs are fairly explanatory. Anything over TCP will benefit there. How exactly are you using Optane PMEM?
So Optane is used as a write buffer cache, and it's used primarily in an on-premise type of infrastructure. With AWS, it's different because our level of redundancy and the amount of time to recover from a failure is lower because we can bring up an instance and replicate data to that much faster than waiting on-premise for a technician to get out there, put a new server in, or swap out an SSD. So with AWS, we don't necessarily need the write buffer cache. The calculations for the reliability are somewhat different at that point.
Okay. And in one of your previous slides, you'd stated that you had intelligent management around reducing wear. Does the Optane factor in there as well?
So what was the end of your question?
How are you reducing the wear?
All right, so that's a very good question. So what we basically do is where everything that you're writing to the disks will be written in Stripe. It won't be random reads, and we're not overriding the drive. So we'll try to fulfill them, and then we'll clean drives when everything gets full, rather than keep rewriting them. So the wear and tear of the SSDs, we have the ability to use the QLC drives and give the same resiliency as TLC drives, which are much more expensive and has less capacity because the amount of writes you can do in each non-cell.
So you're building up chunks of writable data within the Optane PMEM and then deciding where to put those.
That is correct.
Okay.
And back to your question, we do that regardless of the availability of PMM or not.
Okay.
Yeah, so everything is written in the cloud. As Amir was saying, it works a little bit differently because we don't have the ability to control the hardware. So, and they don't have persistent memory available on those nodes. So we consider them differently, where if something will fail, we'll just spin up another instance, we'll replicate the data to it, and we'll resume normal. Even if a drive will die, that's what will cause it, because there's no ability to go and ask someone to swap a drive.
It's fair. And without monopolizing time, how are you implementing that data reduction? Or have you anything coming up on that? I've seen references to compression, dedupe, and fingerprinting. It's kind of
compaction and compression. Do you want
Compaction.
So
on the
what we're doing today is we have compression available and dedupe in our roadmap. So we use compression inline.
okay.
There's no difference. The difference in performance is almost unnoticeable if you turn it on and off. And you can actually turn on compression for specific volumes and others turn it off.
Okay.
Also, you can set up the amount of replications you want per volume. So if you have a volume for compressed media you're unlikely to compress it, right? Because it's not going to give you a much beneficial. So you can set that on or off in this case, and another drive that has database that is highly redundant, you can set compression on and it will give you more reduction. And of course, you can see per volume how much reduction are you achieving and not achieving.
And can that be used as a post-process task? Can you change between states and compression?
You can actually turn compression on or off. It will be changed. It won't rewrite the data, but from a point when you change it, it will start either compressing or not.
All right, thank you.
So let's talk a little bit about a couple more features that you get when you're on the public cloud. So efficiency is one of them. We mentioned, and we just talked about compression, right? Something that you don't normally get if you're doing block storage in the public clouds. Then provisioning, we talked about. The cluster can actually scale itself automatically. So if your cluster reaches a certain predefined threshold that you can determine, it'll add an extra node to itself. If it hits another lower threshold, it can actually release a node from itself. So you're not actually paying for the unused storage. Talked about snapshots and clones, which we found can be a significant cost reduction on the operations of some deployments. Per volume replication policies, Roy just mentioned that as well. And then what this boils down to is you're utilizing much more of the storage that you're paying for. So rather than paying for storage that you provisioned in advance, that you predetermined to decide how much storage you're going to provision, and you pay for all of that storage regardless of if you're using it on day one, with Lightbits, you can actually just pay for the storage that you're using, not for what you've provisioned. So you get a much lower TCO as a result of that. And with Lightbits too, you're not paying for your unit of performance. And so in some scenarios with certain products, you pay for each IOP that you're allocating to a volume. With Lightbits, that doesn't exist. You get the full performance of the Lightbits cluster. And we've seen up to 1.5 million IOPS per volume, which is far higher than what's available today from a cloud block storage product. So if you have applications that are IOPS bound, perhaps you're paying an expensive license for those applications per core, you can now get more performance out of those applications without necessarily needing to deploy more cores driving that application. Latencies are less than 500 microseconds, tail latencies less than a millisecond, so much more consistent performance, much faster. And like I mentioned, you can get more performance from your applications without adding more cores. There's applications that you can get more throughput from without needing to buy more instances or licenses for those. So overall, you're going to be paying less if you're using something like Lightbits in the backend for your block storage.
And just on the volume basis, is there a concept of volume ownership within the cluster? Does that go to a node, or is that spread across all the nodes within a cluster?
So with NVMe TCP, you can attach a volume to a specific client, and it'll appear on that client as if it's local to that volume. There is an idea of multi-attach as well, where you can have multiple clients attached to a single volume.
Within Lightbits, though, providing that volume, is that a distributed function that provides that volume? So
that would go more towards, I believe, multi-tenancy, right? Where you have ownership of specific volumes and access limited based on multi-tenancy.
Are you referring to multi-tenancy in this case, or are you referring of how does a volume attach to a client and working with the Lightbits cluster?
No, I'm fine with that aspect, but within the storage subsystem, if you have a 6-node cluster, does one of those specific nodes have ownership of that volume being presented?
Okay, so that's a good question. So what happens is that when we're connecting, we're defining, or when we're creating a volume, and you'll see that in the demo in a few minutes. Okay. When you're creating a volume, you're deciding how many replicas you want to that volume. But each volume will always have its primary node that it's connected to, and it will always work through that node. When we're creating multiple volumes, our system will intelligently know to balance those between the available nodes based on capacity and utilization. But at a given point, there'll be only one primary node in the Lightbits cluster that is connected to a client and working with that client and serving the data. Okay. The data will actually, I haven't done it in the demo, but I have a live system that I can show you after that. The client will always see the remaining or the available nodes that has that replication as a secondary and maybe a third, depending on the amount of replication. So once the primary goes offline, and the NVMe subsystem will immediately move to work with the secondary node, and the data will continue to be served from another node.
And one last question, does data reduction happen at a volume level or across the entire data set?
So the compression, as said, can happen in a volume per volume basis. You can decide each volume if you want to enable or not. I can't remember if the cluster overall is compressing it across, but I need to check that and get back to you.
So I know.
Yeah.
Thank you.
Sure.
Yep. So one last key set of features that you need to have for a public cloud is ease of use. We all know that many customers use public clouds because they're easy, not necessarily because they're the fast or because they're cheap, but it's easy and it's efficient to deploy on them. So it was our goal to be as easy to use as possible. Obviously, we don't have access to the native AWS graphical user interfaces and consoles, but to make the interface as seamless as possible so that you can use Lightbits within AWS. And so setup through CloudFormation scripts and AMIs can take 15 minutes. You can click through it through the marketplace and install the product as well. Within a couple minutes, have a cluster up and running for you. The same APIs and command lines that you would have if you're running it on premise as well. Management, we automated a lot of the tasks so that you don't have to add and remove nodes to the cluster. All of that is done automatically based on capacity, based on failures, and the level of redundancy you want. Same with the upgrades of the cluster as well. All of that is automated. You're not getting your hands dirty, taking nodes offline and online. And if you want, you can use this on premise and also in the cloud as well. So the same type of interface as well. And just on the right there is the screenshot of our AWS marketplace listing that will go public later this summer as well. So we showed you how we're taking block storage to the next level inside of the public cloud today. We have Roy who's going to give a demo.
I'm going to show you how do we deploy from the marketplace. How do we spin up a Lightbits cluster through the marketplace? How am I'll spin up a client and connect it to Lightbits and run a simple test called FIO. If you're not familiar with it, FIO is a tool to benchmark storage performance. And I hope I'll give you the wow effect with showing you the ability to, out of the box with the marketplace, get 1 million IOPS out of a single volume with a sub-millisecond latency. All right, so let's start with going through the marketplace and just searching for Lightbits, searching for the Lightbits offering. And what I'll do here is I'll choose, we're going to have an offer to own the storage and you'll be billed by the EC2 instances, or to just subscribe and bring your own EC2 instances, which means that it makes sense if you have, if you have dedicated hardware and so on, and you don't have to, you have better prices. So we'll go and start to configure this. We'll configure the way we want to install, the version of Lightbits that we want to install. And just remember, this is a preview. This is going to be available later this summer. So I can use the way I deploy. I deploy through CloudFormation and do launch, which will take me to the CloudFormation if you're familiar with it. And then we have the ability to set up the configuration of the cluster. So I'll just give the stack a name for the CloudFormation to be deployed. I'll choose then my region. I will choose my availability zone. And then I'll define whether I want to use an existing VPC, private subnet, and public subnet in a gateway, or I want to create new. I'll define in this case, I'm creating a new infrastructure completely. So I'll put a new CIDR address range here and continue to set up and to see if I want to have the settings automatically or with existing configuration. I will choose who can access the cluster. In this case, I just gave it everyone can access. Then I will choose the amount of instances that I can run from. I want to run 3 Lightbits nodes. I'm just putting the key. And lastly, I'm putting a bucket to store the configuration of the installation. I'll hit Lex. Here, there are some CloudFormation settings. I will leave this as B. What happens if it fails and so on. I'll go to review the configuration, add tags if I want. And lastly, I will acknowledge the use of resources, and we'll create the stack. That's how you deploy from the marketplace. So what will happen now is that the CloudFormation will go, it will create the network infrastructure. It will deploy EC2 instances as we chose. It will go and install the Lightbits software using actually Lambda functions. And we'll continue by deploying a SaaS monitoring agent that we're developing for that to work. So in the meanwhile, you can see here that it starts initializing. This is fast forwarded, right? The whole procedure takes around 15 minutes from the time you hit launch until it's deployed. In the meanwhile, what I'm going to do, I'm just going to deploy a client for us to use. I'm going to use an AMI that has some pre-existing conditions, but not necessarily the NVMe stack, because that's actually something that is available on all modern Linux distributions. So you don't need to install it in advance. But the things like FIO and our service called Discovery Client, which I'll talk in a second, is already pre-installed. And I've chose the C5N, the biggest instance. It has a 100 gig network, so I can kind of show you more capabilities of the infrastructure and not be bounded by the network. Just the configuration of the cluster, right? I choose the VPC that was created a second ago by the CloudFormation and the subnet. And if I want to have a public IP, I actually didn't use the public IP in this case, but if you want to use it, storage, I just choose the minimum that I can have only for the initialization of that client, because we're going to use the NVMe over TCP stack coming from the Lightbits cluster. Then the security group, we have to enable certain ports for NVMe over TCP to work. So it's all predefined by the CloudFormation and enables the right ports to be working on. That's all there is to it. I can continue and launch my client, just add the key so I can access it. And once this is done, I can go and see what's going on. I'll see that it's been initialized. And now what I'll go and do is, once this is done, let's see what's going on with my CloudFormation. As I said, it's fast forward. And what I'm going to do here is I'm going to connect to the client that I've just created, and I'm going to enable NVMe over TCP to work. It's not enabled by default. You have to probe it. So I will enable it, and I always joke about myself. I didn't remove this from the recording, but I always forget to sudo. So so in order to just enable NVMe over TCP, you'll do mode probe or put it in your RC local to load automatically, and that's all there is to it. So now NVMe is enabled. Now, what we'll see here is if I'll run NVMe list, it will show you that the only device that we currently have is the one that we created, the block storage. It's NVMe as well, but there's nothing coming from Lightbits. So back to the CloudFormation, let's see that it finished. It finished creating the EC2 instances, and then it will, in a second, be completed. And what we have to do here, once this is done, is that I'll go to one of the nodes of the Lightbits cluster. I'll connect to it. Our CloudFormation is complete. It will complete the main. So now, when this is completed, I will go into my Lightbits cluster. I will go into one of the nodes, either one of them. It doesn't really matter. I'll connect to it, and what I'll do first is I'll show in that cluster. I need to enable or add a JOT token. So the token is the key that enables me the ability to run LB CLI commands. So we do support CLI or REST API. In order to do that, I need to enter the token into a YAML file within one of the nodes that I want to work, or I can do it actually from remote from a client. I can add the same LB CLI with that token. So all I need to do is just here take that token that is being added to all the nodes of the cluster automatically when we're doing CloudFormation. So I'll just copy that and place it on that YAML. And once I'll do that, I can go and run the LB CLI commands with no problem. So after I did that, and I just want to show you, I left this because I wanted to show you that there's nothing else, right? There's nothing that I've trimmed away. This is how we actually install and get a cluster working for us. So now if I'll do LB CLI list nodes, we have 3 available nodes. They're all active and healthy. I have the NVMe IP endpoints for them so I can connect to them. And what I need to do now is I actually need to create a few volumes because I want to connect to the volumes. So in order to create volumes, what I do is I use the LB CLI create volume command. And what I do here with, if we have multi-tenancy, I can have different projects. So each volume will be assigned to a project. I'll leave it at default, give the volume a name, give the volume size. Sorry, first I'll do the ACL. The ACL is equivalent to what you know from the fiber channel world, which is zoning and masking. So you just define a name so you can connect to that set of volumes. You put the size, thin provision all the way. So I put a 1 terabyte volume. And then I'll say how many, if I want to enable or disable compression for this volume, as we said before, so per volume. And lastly, I will say how many replicas I want this specific volume to have. In this case, I've chose 2. So it means that 2 of the nodes will have a replication of the data. I'll hit enter here, and it will be immediately created for us. And just for the sake of it, I did create 2 volumes. So I hit enter, it created that, that volume. Don't worry about the protection state. In a second, you'll see that it's actually created. I've added another volume called CD2, and now I have 2 volumes. I'll issue LBCLI list volumes, and I'll see here that I have 2 volumes that are available, have the right size that I've created, compression as I set up, and they have the ACL. Now, what I need to do is I'll go back to my client, and I'll connect to the Lightbits cluster. In order to do that, I'm going to use a tool called a discovery client. This is a service that we have, but we don't have to use it. The NVMe stack that is coming with the Linux kernel can support connecting. It's just that our discovery client is easier to sustain and have persistency of our volume, but you don't have to use it. In order to connect, as we've seen again before, we don't have any other volumes here. So in order to connect the volume, what I have to do here is run, I scrolled up to see the IP address of one of the nodes. And what I do here is I run the discovery client, and I do connect all. So connect all. I do connect all, and I define the protocol, which is TCP. I define one of the IP addresses of the cluster. It will discover the rest. I set up the ACL. So I did client 1. I had 2 volumes, again, client 1, and I do -P for persistence. I'll hit enter, and you'll see that it found 3 instances. Each one of them is one of the Lightbits nodes. And now, if I run NVMe list, we have 2 devices that are coming from Lightbits. It's connected. If I run lsbak, which is the Linux native command, Linux sees it as another 2 physical disk or drives that is available for usage. And now for a little bit of the fun part. So I told you about FIO. What I'm going to do here is I'm going to run FIO running 4K blocks for 15 seconds, 100% read from one of the volumes. And with that, you'll be able to see that you'll get more than 1 million IOPS out of this. So I'm just running 4K, 100% read from one of the devices that I've chose, and running it for 15 seconds, as I said. And out of the box, with no tuning, no configuration, you get almost 1.1 million IOPS. And the throughput is around 4.2 gigabytes. And once this summarized, we'll be able to see that the latency, the average latency is 0.7 millisecond with this million IOPS. The tail is around 2 milliseconds for this specific workload. And the bandwidth, as we've seen, is around 4.2. So for just to make it a little bit more interesting, what I did is I actually ran the same thing with 8 kilobytes. So I'm not expecting to get the same amount, but still with changing this to 8K blocks, I'm getting 750,000 IOPS, more than that. And the latency will be slightly up because obviously, the block size is a little bigger, but still, as you see, the throughput is 6 gigabytes per second on this, and I can stretch this more. And still, the latency here is around, the average is around 1 millisecond with a tail of 3.5 milliseconds. Now, one note, I'll pause this because this is the end of this video, and I have a system live if you want to see additional things. But this is running against the previous generation of Intel. If we're actually running the Ice Lake, we get much better performance, and the latency is increased significantly comparing to this, as Vivek was saying earlier.
Specifically, what's giving those performance gains within Ice Lake?
The Ice Lake CPUs are better performance. Maybe Vivek can answer that question more than I am, but it's a matter of it's a newer generation and better performant CPU. So per core, it's better performant.
How the memory bandwidth utilization is happening, better core performance that's there as part of the Ice Lake, and the software optimizations that goes in on the Lightbits stack contributes to some of the performance improvements that Roy is mentioning using an Ice Lake platform.
Okay.
I mean, I would say that the architecture-wise, I mean, I'm still grappling or thinking in my head as to why not the placement group. I'm still stuck on the same thought because it's available, and if you're putting all the freeze nodes and you have no control otherwise as to why they're somewhere else, I can understand if you're not hitting the, say, network requirement. You know, if you're not hitting that limit, maybe there's not much benefit in having them so in a placement group from that point of view. But again, putting them there puts some control over it as to them being together.
So there again, you have the as Eran was saying, Eran said that the customers have the flexibility. So you do have the option to choose whether you want it or not. We didn't see that much difference. And one more thing that is somewhat, in some cases, challenging is think about that you want to deploy a large amount of instances in the same placement group. In some cases, we've seen that you won't be able to get the resources. So it's a trade-off of what you want to do and how you want to deploy, and we can decide if we want to do it in some cases or not. You know, if customers have pre-allocated instances that will be reserved for them, maybe they can put it in the placement group because they own the hardware or own the reservation. In other cases, I was trying to deploy, and in some cases when I tried to deploy in the placement group, it didn't work, or that I deployed it with some clients and the clients were not on the same placement group. So I'm not sure if there was that much of a gain in performance, because if your clients are on the other building, you'll get that latency.
Right. Maybe it can be an optional feature.
Yeah, it's an option. You can set it on or off. We'll be able to, I'll take it back, and we'll be able to, when you deploy, say if you want it in the same placement group or not.
Quick question: the multi-AZ thing. Am I right in understanding that you are actually going to make it available with all those caveats that you mentioned? Obviously, we understand those.
We will have the option to both back up to S3 or back up to have a stretch cluster, if you call it, between availability zones, with the caveat of the fact that you're going to get a performance hit. So right. It's not right for every performance, right? We're focusing on getting you high bandwidth and low latency with small block size, which is sometimes very difficult to achieve. And if you're starting to stretch and you're getting stretch a cluster, you're getting even sometimes 5 millisecond latency in this type of environment, of a high performance environment, could be degradation in performance that would be too significant to justify the system.
And I assume all replicas are synchronous.
All replicas are synchronous between within that cluster. Yeah, it's not something that you manage or not manage. You set up the replication and it will be synchronous. So when you're writing data, when you're writing a block, you'll get the acknowledged back to the client once all the replications were fulfilled or secured.